Hello, and thank you so much for joining me for this talk on geomorphological hazards in deserts. The world of deserts is very different from the world many of us know. And when I was an undergraduate 50 years ago, one of the Cambridge professors said that physical geography was becoming less and less relevant to humans as more and more of the world became like Luton. Luton is shown here. But of course, that was not true. The fact is that desert environments are very different from those that most of us experience. Deserts are also hugely important. They cover about 1/3 of the Earth's land surface. They're home literally to billions of people. They contain some of the world's great mega cities with populations of 20 million or 10 million or whatever: Cairo, Lima, Karachi, Tehran. And of course, desert areas are at the present time developing very fast as hydrocarbons such as oil are exploited. Lithium is obtained from salt lakes to power your mobile phones. More and more interest in renewable energy generated by wind and solar power, which are both very prevalent in deserts. And of course, the growth of tourism. Deserts are also important because what goes on in deserts can affect the whole world, and in particular, the blowing of dust from the heart of deserts can affect world climates. Now, deserts are becoming, as I say, increasingly utilized, and one only has to go to somewhere like the United Arab Emirates to see the way in which the landscape is being transformed by human activities, as material is won from sand quarries and taken off to Dubai itself to create islands offshore. And here is a satellite image of Dubai in 1984, at the very beginning of its boom, and then in 2016, when a huge array of islands in the shape of palms on the map of the world have developed offshore. And not only are we getting all that development of islands offshore, but we're also having in the Middle East, in the Arab world, a great increase in the urban population. More and more people are living in cities. The cities are getting increasingly large. So in 1950, less than a quarter of people in the Arab world lived in cities. By 2030, it should be well over 2/3. So lots and lots of people living in deserts, and more of them living in cities. And they are exposed to a whole array of different hazards, which are particular to deserts. Curiously, given that deserts are meant to be dry, flash floods and the boulder transport they undertake are very important. Slopes can be very unstable. Rivers can cut down and create gullies and intense soil erosion. Dunes, sand dunes, can migrate at frightening rates. The ground in many desert areas is subsiding for a variety of reasons. Lakes may flood, lakes may dry up, may desiccate. And we get dust storms, which can be extremely hazardous, and engineering structures and buildings can be attacked by severe salt weathering. So I'm going to talk about a variety of these desert hazards. First I want to talk about is floods. It has often been said that one of the problems with water in deserts is that there's either too much, too little, which one would expect, and too dirty. And floods are a major hazard, and it's for this reason that when we go to many desert areas like this part of northwest China, one finds heroic engineering structures have been built like this concrete-lined channel to try and reduce the risk that flooding poses to the people of this area. And when one drives around the American West, driving down in one Chevy, one finds signs like this: "When flooded, turn round, don't drown." And I can show you a whole series of slides of flash floods taking place in deserts. This is an example from the Atacama Desert in Latin America in March 2015. And here is another example from the Atacama in February 2019, and from Kandahar in Afghanistan in March 2019. Here's 2019 in Iran again, with this hugely turbulent river charging through what is an arid landscape. And here's the latest slide I've got of a desert flood. This is a location called Hail in Saudi Arabia, January this year. So these floods cause great damage. They can cause great death. They also can carry huge amounts of debris, and some of this debris is very coarse, occurs in the form of boulders. So here is a river in the United Arab Emirates without a flood flowing down it, but you can see that the base of the channel is composed very largely of huge rounded boulders. And when this wadi, that's what we call desert rivers, floods, these boulders start to move. And this is a picture I took in Tunisia, showing a pier undermined on a road bridge. You can see that under the figure who's standing on the bridge, and that damage is caused by boulders like this. And the engineer in this case who built the culvert plainly was not aware of the very large size of the debris that can come down the channels. So why do we get these flash floods in deserts, which are meant to be dry, and why do they carry so much debris? Well, there are a variety of reasons for this. One is that one does get occasional heavy storms in deserts, and these generate runoff, particularly from surfaces which have low infiltration capacities. And low infiltration capacities exist in deserts because the surface materials, the soils, have very little humus in them, and they have they're relatively impermeable, so that when rain falls on them, you get runoff occurring. And in particular, we get a lot of silty surfaces in deserts which are impermeable because they're battered and splattered by raindrops, which make them impermeable to infiltrating water. So these are some of the reasons we get flash floods in deserts. And this is what I've just been saying about rain splash on bare soils with a lack of vegetation, causing sealing of the ground surface and thus a low infiltration capacity, which generates runoff. Now, I said that you get occasional rainy days in deserts, and indeed you can get tens and hundreds of millimeters per day of rainfall on occasions. But actually, most desert rainfall does not occur as great whopping storms. It's rather more gentle than that. And you can see some figures here for Oxford, London, and Manchester, compared with Death Valley, North Africa, and Dubai. And the figures are relatively similar, but even some of these quite small falls in deserts can generate runoff because of the infiltration capacity characteristics that I've already mentioned. There is one other factor which also encourages flood risk. A lot of work's been done on this in the American West, and this is fire. When fires occur in resinous desert shrublands, they affect the nature of the soil, which affects runoff. And we have a situation where not only does the fire increase runoff, but it also can cause slope instability. And I'll explain that now. But here's a picture from 2020 of a fire taking place above a patriotic homestead in California. And then after the fire, you have floods, but these floods also carry a huge amount of mud, creating mudslides and mud flows. And this is because of a slightly complicated process called hydrophobicity, or in more usual English, water repellency. Hydrophobic soils repel water. A thin layer of soil at or below the mineral soil surface can become hydrophobic after intense heating by fire. The hydrophobic layer is the result of a waxy substance that is derived from plant material burned during a hot fire. This waxy substance penetrates the soil as gas and solidifies after cooling, forming a waxy coating around soil particles. And it's this that causes the soil infiltration capacity to be reduced, and therefore you get erosion of this upper layer of material, which forms the mudflow substance. So here we have a mini car in South California in October 2015, which was caused in a mudflow. And mudflows really are like ready-mix concrete in terms of their consistency. Lots of sediment, lots of water combined, and they are extremely dangerous, as you can see. And a more up-to-date picture of Monterey in California, showing again the effects that a huge mudflow have had on this particular settlement. And all over the desert realm, we see the evidence of mud flows, and many of the alluvial fans, which we see so often, are largely formed by mud flows. So if you build a road, as we see here in Death Valley, California, going around the base of the alluvial fan that comes down from the mountain front, that road is, of course, at considerable risk. Here's another debris flow horror story from Peru in late March 2015. And some of these slope instabilities are not, of course, caused just by fire. They can be caused by an array of human activities. And this is an example from the Lanzhou area in China, where you have a huge amount of wind-blown silt that's accumulated over millions of years called loess, or loess. And in this particular case, the farmers have irrigated fields on the top of the plateau, which is composed of the loess. And the water from the irrigated fields gets into the loess, which is a very weak and feeble sort of material, causing slope collapse. And there is the track of a large slope collapse, which brought material right across the valley. So there in the background, you can see that slope, that plateau where the irrigation took place, and this mass of material came right across the valley and up the other side, transporting a van in the process. Another feature of the fluvial environment in deserts is that it can be very unstable, in that you get spasms of cut and spasms of fill. And here's an example of gully formation in Swaziland, in a semi-arid area in southern Africa. Swaziland now called Eswatini. And you have soils here which are very weak, and when you get a storm, then the runoff cuts down into that weak material, creating this badland environment. And such badlands are very widespread in many parts of the arid realm. So that's enough of rivers. What about sand? Well, obviously, large tracts of desert are characterized by moving sand dunes, and these create problems for humans. partly because the dunes themselves can encroach upon engineering structures such as roads and canals. But sand is also abrasive. And if you have strong winds carrying a lot of sand, it can attack buildings and other engineering structures. So here is a picture from the American West showing the material that can be transported in strong wind events. It can be quite coarse. Here's a car windscreen on the left that's been crazed by almost pellet-sized, gravel-sized material being whipped up by the wind. And even in one case, the wind transported a rabbit and wrapped it around a telegraph pole, as you can see bottom right. So sand dunes can encroach upon roads, and in particular, we have various types of mobile sand dunes called barcans, which are crescentic little dunes. They can be crescentic, quite big dunes, and they move fast and they encroach upon engineering structures. And top left, we have a railway line in Namibia, and that railway line had to be diverted because of barcans moving across it. And in a dry environment with very little vegetation and with strong winds, dunes and sandstorms associated with them can be really quite prevalent and frequent and dangerous. This is an example in Namibia of a building that has been scoured by the abrasive effects of sand. You can see the eroded right-hand corner, for example, of that building. And you can also see the sand accumulating inside it. Much more dramatic is this picture taken from the air of a main superhighway in Dubai, with all this sand coming across it after a sand event. As I say, some of the most mobile dunes are barcans, crescentic-shaped dunes, horny little beasts, where the points of the dune are in the direction of travel. And here we have dunes coming from the north in the Karga oasis in Egypt, encroaching upon roads and railway lines. And the reason there are so many railway lines there is that they've had to be moved from time to time as these barcans have encroached upon them. And in many parts of the world, because of the threat that they pose, sand dunes are being stabilized by a whole series of methods, like building sand fences, creating checkerboards of straw, and by irrigating plants. This particular example is in northwest China, and what they're trying to do is to stop sand encroaching upon one of the most important religious and archaeological sites in the region. But it's not just sand-sized material that's a problem in deserts. Also very hazardous, perhaps even more hazardous, are dust storms. These transport material which is about the size of talcum powder, say 5 to 50 microns, something of that sort. And again, because of the lack of vegetation in desert surfaces and because of the lack of binding humus and so on, when you get strong winds, then dust storms occur. And they can reduce visibility right down to almost nothing, though they're normally defined as being events which reduce visibility to less than a kilometer. So here we have the Emirates Highway near Dubai Airport. Don't do this at home. You shouldn't drive and take a photograph at the same time, but that's really rather dramatic. Some of these thunderstorm-related dust storms are called haboobs. And when you get one of these dry thunderstorms occurring, you get a lot of convectional activity, which pulls up the dust from the desert surface. And here is an example from the outback of Australia. Another haboob coming across the city of Phoenix in Arizona in the USA. Another event in Texas on July the 9th, 2019. another event in New South Wales in 2019. And such was the reduction in visibility. In this case, you couldn't see the bonnet of your car, so you shouldn't, of course, be driving it. So this huge pall of red dust swept across this part of South Australia just a couple of years ago. And this is my latest slide of a decent dust storm. This is Las Vegas in Nevada in the USA in February 2021. Oh, and here's an even later one. This is Beijing, March 2021. So these great cities in Australia, in China, and in the USA are afflicted by dust storms. And these dust storms are nasty because not only do they reduce visibility, which creates accidents and affects airline operations, but dust can be extremely nasty in terms of health. And the number of days upon which dust storms occur can be considerable. This is just a fairly random selection that I've put together from the literature, but you can see that dust storms can occur on tens of days in the year, reducing visibility to less than a kilometre. So they occur with considerable frequency. They carry a lot of material, some billions of tons per year in the world, and much of this dust is transported from the deserts over huge areas, which is why it has an effect on global climate and global conditions. So we find that dust from the Sahara goes across the Atlantic to Amazonia, the Caribbean to the USA. It even comes to the UK. Dust from Patagonia gets to Antarctica. Dust from the USA gets to Greenland. Dust from China goes all the way around the world. And dust from Australia gets to New Zealand. And these events are frequent, carry a lot of material, and they're spatially very extensive. So here's a satellite image of a great dust pall coming out over the Indian Ocean, the Gulf of Oman, from the inland dry areas of Pakistan and Afghanistan and Iran. So the environmental effects of these dust storms are considerable. They can cause climate change in a variety of ways. They affect the amount of radiation coming in from the sun. They also affect cloud formation processes. And the general view, in fact, is that dust storms make dry conditions worse. They exacerbate drought. They also carry material which affects soil. Some of this is for the good, but the soil can also have a lot of salt added to it by dust storms, which is bad for plant growth. They can also carry all sorts of diseases, allergens and things of that sort, silica dust, which causes silicosis, and so on and so forth. They can affect the world ocean by giving plankton a dose of nutrients, which can have all sorts of climatic and biogeographical results. Dust from deserts can go all the way to the polar ice caps, and they cause the dust, the ice to become dirty, changing the albedo, making the ice cap less reflective of incoming radiation, so the ice cap can absorb more temperature and therefore melt. And we have things like air pollution in cities like Beijing, and also we may get changes in the acidity of rainfall, which may in fact be a good thing. But there's a whole series of human health implications. In the American West, there's a disease called valley fever, caused by the movement of allergens derived from the erosion of soil by the wind. In Nigeria and other parts of West Africa, we get meningitis, particularly in the spring, when the dust storms called the harmattan, again, bring material from the Sahara into the Sahel, into areas like Kano in northern Nigeria, and you get hundreds of thousands of cases of meningitis. Conjunctivitis, caused by nasty things in the air, affects people's eyes. Lots and lots of dust in the atmosphere is very bad for your breathing, and it also affects your heart. Particularly the smaller particles in the dust can get into your circulation system and cause heart attacks and the like. And here's a nasty slide from the American Southwest of a poor lady who's been afflicted by valley fever. And on the right, you see a bad dust event on the interstate highway in which a lot of people died. It was rather like driving in fog, but it was dust. So the lesson is, do not overtake in dust. And of course, in history, there's been some enormously serious dust storm episodes. The most famous of these is the Great Dust Bowl itself of the 1930s in the American West. A huge area was affected by dust storm damage in Texas, New Mexico, Colorado, Kansas, Oklahoma, particularly. Huge area. It was very hot. It was very dry. It was very windy, and the ground surface had been plowed up in the good years, and this exposed the soil to wind attack. And people had a hard time in the 30s in the American high plains. There was one man who found it was so hot that when he went to bed, he decided not to go to bed, but to put his head in the Kelvinator refrigerator, which he did to try and cool down, and he never woke up. And here are the refugees, the environmental refugees. They were called Okies. They came from Oklahoma, and they drove off in their old jalopies to get away from the horrors of the Dust Bowl region. And the dust comes from a whole series of sources. It's particularly serious in the Northern Hemisphere, particularly serious in the vicinity of old dried up lake beds, particularly serious in really dry areas, but also serious from various types of alluvial fan and so on. So here is a picture of the Seistan Basin at the borders of Pakistan, Iran, and Afghanistan, an area called the Hamoon Lakes. And these flood, dry out. They get loaded with silt by the Helmand River, which comes in, as you can see, from the east, pumps this silt into the lake basin. The lake basin then dries up, and all that silt is then available for movement by northwesterly winds that blow on 120 days in the year and create all sorts of health problems. And here's, again, plumes of dust coming off an old dried up lake bed in the center of the Sahara from the Bodele Depression in the Republic of Chad. And you can see a series of dust pools there blowing across the desert surface. And it's this sort of dust that transports meningitis or causes meningitis in northern Nigeria. And again, humans play a role here. I've mentioned plowing up of the land, and obviously removal of vegetation, disturbance of the ground surface by various human activities does increase the likelihood of dust storms occurring. And some quite interesting work, very interesting work has been done on dust production per year in North Africa. And we see figures here in millions of tons for the period from the 1940s to the 1960s, 126 million tons. By the 1980s and 1990s, this had gone up to 10 times that figure. And in one particular year, 1984, it had gone up even higher. Now, there are various reasons for this. One is natural in the sense that in the late 1960s onwards, we had a period of extreme drought in this part of West Africa called the Sahel drought. So this reduced vegetation cover and made the soils dry out. But it was also, of course, a fact that human populations had grown at the same time, causing deforestation, overgrazing, and so on and so forth. And in similar vein, in the American West, areas like the Owens Valley, inland from Los Angeles, on the eastern side of the Great Sierra Nevada mountains, Owens Lake has been desiccated because water has been removed from it to be taken by great canals to provide water for the growing city of Los Angeles. And it's therefore not surprising that as that lake bed became exposed by desiccation, you got more and more dust storms occurring. And some of the dust is extremely nasty in that it carries some rather nasty chemicals from the floor of the lake, including arsenic. Another reason why humans are exacerbating the problem is by disturbing desert surfaces by driving over them. This is a picture in the Western Desert in Egypt showing a Toyota that has come across the desert surface. And that desert surface has a lag of coarse material that has accumulated over the years as the fine material has been blown away by the wind. But if you disturb that surface lag, you expose the finer material beneath, and then it can be evacuated by the wind in dust storms. And this process has been called Toyotarization. And there is a Toyota for scale. We also disturb the desert surface in other ways. And this is an example from Oman, where the ground has been scored by a series of rectangular patterned seismic lines. These involve clearing the desert surface so that you can search for oil using seismic techniques. So that whole surface has been changed. So we've had water effects, we've had the effects of wind. Another very important hazard type in deserts is what I call salt attack. Deserts are dry, therefore soluble materials tend not to be removed by rivers and taken to the sea as they might be in the UK. Salt accumulates, particularly in the many closed basins that occur in desert regions. And from those desert closed depressions, the salty silts can be transported by dust storms and cover the area more extensively. And because of very severe evaporation, any water, particularly groundwater, migrating up to the surface by a process called capillarity, can become concentrated as it evaporates under the desert heat. And salt weathering is quite complicated. There are various different types. It can be a physical process involving the growth of salt crystals from solution or hydration in building materials in response to temperature and humidity changes, or it can be a chemical process involving reactions with, for example, minerals in cement and with iron reinforcements in buildings. So salt accumulates in closed basins. Lovely picture here of a man reading a book floating in the very dense waters of the Dead Sea. And this is Death Valley in California. Again, you can see the vast area of whitish sort of ground in the middle background, which is salt accumulation. And there's me as a younger man for scale, because I did some work here on the effects of this salt on the alluvial fan material that came into the salty basin. So we have natural saltiness in deserts, but again, humans are making it worse. And one way we've done this is through the spread of irrigation. This is a canal radiating out from the Indus River in Pakistan. It looks very nice, doesn't it? It could be the River Thames flowing through Oxford almost, but of course it isn't. So there's that lovely water coming down to irrigate the fields. But if you turn your back, here you get a very different picture, because the irrigation water spread over the fields evaporates and the salts within it accumulate. It also raises the groundwater level, and the groundwater moving to the surface by capillarity also evaporates and becomes more salty. And in fact, large areas can become waterlogged. And all the whiteness in this particular picture is caused by salt. This is very deleterious for public water supply, of course. It's very deleterious for drinking water for domestic stock. It's very deleterious for crop growth. It effectively stops it, and it's very deleterious for any buildings that may exist in the area. So we get salt accumulating as a result of irrigation. It can also accumulate as a result of land use changes, and in particular, deforestation. The presence of a tree cover reduces the amount of rainfall that hits the ground surface, and you get what's called interception. And then you are in a situation where you get a lot of evaporation, and evapotranspiration of moisture, which means that the groundwater level is quite low. When you cut down all that vegetation, you get more rainfall hitting the ground surface, less loss of water by transpiration. The groundwater level comes up, and it brings the groundwater up to the ground surface, where it can evaporate and become much more salty. So we have a process of what's called dry land salinization, and this is hugely problematic in Western Australia. And we know, going to desert areas, that many of the rocks are severely weathered. Here's a Tafoni. This is a sort of cavernous, hollowed out boulder in Chile, which has been attacked by salt. And here is a boulder in Death Valley. Great big boulder came down with a mud flow from the alluvial fan, came into that salty bottomland I showed you earlier, and has begun to disintegrate in a fairly dramatic fashion. And I've put out blocks of rock in desert areas. This is Tunisia, on salty surfaces to see what happens. And you go back 2 years later, and that is what has happened. A very rapid process indeed. And we can simulate the effects of salt getting into the pores of materials in environmental cabinets. You can change the temperature, you can change the salinity, you can change the humidity. You can put blocks of rock or concrete or whatever in the environmental cabinet and see what happens. And sometimes the results are dramatic. These are some experiments I did over 50 years ago with chalk, which of course is quite a weak rock. And I subjected it to a series of different salt treatments. And to cut a long story short, quite a lot of the blocks broke down within a matter of days in response to the effect of crystal growth and hydration, particularly of salts like sodium carbonate, sodium sulfate, sodium nitrate. And we see the effects of this in buildings, ancient and modern. This is Luxor in Egypt. You can see the white efflorescence, the white salt associated with rising damp. These sphinxes are being attacked by salt. And this is due again to the spread of irrigation, higher groundwater levels, bringing salty water up into these buildings. This is one of the great archaeological sites of the world, 4,000-year-old site in Pakistan called Mohenjo-Daro, built of burnt brick. And it was excavated from the 1920s onwards. And the people who excavated it said how wonderfully fresh it was. But since that time, irrigation has spread with all those canals from the Indus. The groundwater level has come up. It's brought pernicious salts into the dried mud bricks and into the burnt bricks, and they have been disintegrating like crazy. And this is a modern building afflicted by salt. This is the nurse's home, which I used to walk around with Sir Ronald Cook in the island of Bahrain in the Middle East. And you can see the pillars are beginning to go. The staircase is beginning to go, and it had to be abandoned. This is the building in Ras Al Khaimah in the Emirates, which was never completed. Again, you can see the appalling state. The salt has attacked the concrete, it's attacked the steel reinforcements, and that building was never used. Here's a wall in Ras Al Khaimah with Professor Dennis Brunsden for scale. And again, you can see the effects of water migrating up from a damp surface into the structure, causing it to develop holes and to lose some of its plaster. So this, again, only a couple of years of action needed for that. Equally dramatic is pipeline in Namibia, designed to take water from an aquifer, that's a groundwater reservoir, to a uranium plant and to one or two of the local towns. And these pipelines were made of concrete, reinforced with iron reinforcement. They were put in the ground, and within 2 years, again, they were totally rogered and had to be abandoned and lifted out. And these are the remains of them. Again, Ras Al Khaimah. Note the water level. There's a pad of gravel, and there is a nice new villa built upon it. What a ridiculous place to build. Because inside, there it is, with the rising damp coming up from the groundwater, transporting the salt, getting into the walls, and again, condemned before it was ever completed. So we can advise people where to build and where not to build in desert areas, but the key thing really is to keep away from shallow groundwater areas, because that's where a lot of the salt comes from. There are some areas in deserts which are relatively free of weathering. And this is an example from Egypt, where the great carvings at Abu Simbel were for many years protected from weathering by being covered over by blown sand. And there are various things we can do to try and reduce the effects of salt weathering. We can try and reduce seepage from canals, sewers, water pipes, and reservoirs. We can try and restore native vegetation, as is the case in Western Australia, where they're trying to get back the eucalyptus in areas where it had been cut down. You can try and reduce groundwater levels by pumping groundwater out through tube wells. That's being done at Mohenjo-Daro in Pakistan. There's been some success in planting plants that accumulate salt, and you then burn them, and the salt occurs then at the surface as ash, and you put that in a wheelbarrow and take it away. And also we need to apply less water if possible to our plants in deserts and our gardens in deserts, where possible use drought-tolerant plants. Another hazard that's very common in deserts, not least in the American West, is ground substance. As one extracts water from groundwater reservoirs, a vacuum is created, nature abhors a vacuum, and the ground begins to sink. The same happens when you exploit oil. You create a vacuum and the ground begins to sink. And some of the figures for the amount of ground substance caused by water abstraction are really pretty dramatic. Mexico City, 7.5 meters. That's the height of an ordinary house. Central Valley, California, 8.5 meters. And we're doing an awful lot of removal of groundwater for irrigation. In the American West, for example, there are systems called center pivot irrigation schemes where you get great big revolving booms spreading water across the desert surface. They enable you to grow crops where you couldn't otherwise do so. And one sees dotted across the landscape great big round circles, which are the areas that are irrigated. And if you look at Google Earth for Saudi Arabia or Libya or the American high plains, you'll see these great circular areas looking like Smarties across the desert surface. Huge amounts of water being exploited in that way, the groundwater level plummeting. And here is the substance that goes with it. This is the San Joaquin Valley in central California. At the bottom, you can see the date 1977, which presumably is when this image was taken. And then as we go up the power pole or telegraph pole or whatever it is, we find the ground surface level in 1955, and then towards the top, the ground surface level in 1925. Similar exercise shown here. We have the situation in the San Joaquin Valley with some recent data on the amount of substance that has occurred. Another hazard, which is fairly significant, is that in deserts you have closed basins. And when water flows into them, they flood. And when there's no water flowing into them, they dry out. So we get lake fluctuations taking place in the many, many closed basins you get in desert regions. This is Death Valley, California. I showed pictures of this earlier. Bad water. In 2007, completely dry. Go to 2019, there is bad water, flooded. Lake Eyre, Australia. Enough water to fill Sydney Harbour 7 times, flowed into Lake Eyre between February and May in 2019, leaving it almost filled for the first time since 1974. This is a picture this year from the Sossus Flay, a river valley flowing into the dunes of Namibia, January 2021. So you get natural fluctuations caused by rainfall events coming and going. But again, humans have played a role, and we get increasing desiccation of some lake basins because water flow into them has been reduced by the construction of irrigation systems, dams, and reservoirs. And the most famous example of this, known to you all, is the desiccation of the Aral Sea in Central Asia. Once a very large body of water with fishing boats and so on, it's now a shadow of what it was. So here we have a satellite image of the Aral Sea in 1989, and we see it again in 2014. And one of the consequences of the Aral Sea drying up is that there are large areas of silty, salty ground that get exposed to wind attack, and you get dust pools coming off downwind. And that dust can carry large amounts of herbicides and insecticides and so forth that were used in the agricultural process, and they are very bad for human health. Yet another example, Lake Chad in 1972, Lake Chad in 2018. Another dramatic example, Lake Urmia in northwest Iran in 1998 and in July 2014. And again, dramatic increase in the amount of dust storm activity to which citizens are exposed downwind. This is a picture of this. It's a bit complicated, but basically, as the water level shown in blue has gone down and the dust shown in black and red has gone up. This again is largely due to the effects of removing water for irrigation and water supply. So then we have a huge array of desert hazards, which make deserts so different from Luton. I've talked about flash floods. I've talked about slope instability. I've talked about gully formation, dune migration, dust storm generation, salt weathering, ground substance, and lake level fluctuations. And one question I leave you with is, how many of these have been made worse by human actions? I might also add, how many of these may be made worse by future climatic changes? So thank you very much indeed for your attention. I hope you've enjoyed some of the desert landscapes I've been able to share with you.
Brilliant. You press anything in meeting 4.